Hello everyone, my name is Emma, and welcome to our third Sammamish Teen Science Cafe Science POV series talk. The Science POV series is aimed at bringing student experts in various science fields to not only talk about what they are passionate about, but also how they explore such interesting avenues of science as a high schooler or college student. We are doing this series virtually, of course, because of the COVID-19 pandemic. We hope all of you and your families are safe. Today's speaker is Christine Yee. Christine Yee is a rising junior at Eastlake High School. Her scientific and research interests include high-energy astrophysical phenomena, compact objects, gravitational waves, cosmology, and astronomical big data. Currently, her work focuses on pulsars, including radio-based search pipelines, as well as glitches and microphysics. For her research, she's been recognized as a special award winner and two-time finalist of the International Science and Engineering Fair, ISEF, representing Washington State, among other honors. So without further ado, please welcome Christine Yee.
Hi everyone, my name's Christine Yee. I'm a student at Eastlake High School, and today I'd like to tell you a little about the wonderful world of gravitational waves and the stellar graveyard. Before I start, I just want to mention that if you have any questions, feel free to contact me via email or Instagram. First, let me introduce myself and my journey in science. In elementary school, I actually wasn't much of a science enthusiast at all. I didn't really like the curriculum we followed or the experiments we did, things like building makeshift maglegs and growing alfalfa plants, and didn't pursue it at all outside of class. But I attribute my getting back into science to an amazing competition program called Science Olympiad. I joined it on a whim in middle school, and by having the opportunity to learn and compete in topics like earth science and meteorology, I found that science was so much more than the exposure I got earlier on. And thanks to my discovery of the beauty of the universe beyond Earth, as well as being surrounded by peers curious about science and space, I became really interested in physics and astrophysics. Although my research interests lie away from instrumentation, I'll always be grateful to the astrophotographers and observers that create beautiful images like these, which first got me into space. Nowadays, I'm interested in a broad variety of topics in physics, most of which would be considered astrophysics. In particular, I'm most interested in the study of compact objects in extreme environments with gravitational waves, and especially with pulsars. Aside from that, I'm also broadly interested in the high-energy universe, such as active galactic nuclei and supernovae, and the application of computation and data science to astronomical big data. Other subfields I find interesting include the study of stellar variability in stars young and old, and cosmology, particularly the growth of large-scale structure in the universe. In my talk, I'll first cover how we observe the universe most of the time, and talk about what makes up the so-called stellar graveyard. I'll also explain the science and strategy behind today's gravity-based observatories and how you can get involved with them. Astronomy is one of humanity's oldest sciences, and even ancient civilizations were fascinated by the night sky. In classical Greek, Chinese, Indian, Arab, and other civilizations, ancient astronomers cataloged the stars, identified planets, which they called wandering stars, and theorized about the true nature of the universe. With the scientific revolution came Galileo, the first person to point a telescope at the night sky. Identifying the orbits of Jupiter's moons, he not only transformed our understanding of our place in the universe, but kicked off an era of telescope-based astronomy. Today, scientists have built amazing instruments on Earth and even orbiting in space, including the famous Hubble Space Telescope, as pictured. These are truly marvels of modern engineering. And the future is extremely bright for observational astronomy, with new instruments and surveys such as the Legacy Survey of Space and Time at the Vera Rubin Observatory, which will scan the entire sky every 3 nights for 10 years, in some of the fastest and deepest scans ever. Astronomy has come a long way from the days of Galileo. Nowadays, astronomers observe the universe at every wavelength of the electromagnetic spectrum. The night sky, and the telescopes we use, look different at every wavelength. At the highest energies, we use things like giant tanks of water and orbiting satellites, and at the lowest energies, we use enormous radio dishes deep in the mountains. Looking at the sky at just one wavelength is like seeing in just one color. With multi-wavelength observations, we get a much better picture of the universe. But there's another invisible messenger from the cosmos, and that is gravity. In the 17th century, Isaac Newton described gravity as an attractive force. His description was remarkably accurate and still holds up today. But in the early 1900s, Albert Einstein published his theory of relativity and revolutionized our understanding of gravity. His theory states that mass tells space how to curve, and space tells mass how to move. Interactions such as the orbit of the Earth around the Sun come from the Earth tracing the shapes the Sun creates in the fabric of space-time. A direct consequence of this theory is the existence of gravitational waves. Gravitational waves are ripples in the fabric of space-time that travel at the speed of light and carry information about the system that created them. Every accelerating mass produces these ripples, but they're extremely hard to detect from Earth. Let's take a step back and talk about stars. Stars are born in the depths of the galaxy's coldest, densest gas clouds. Beginning their lives as temperamental protostars, they evolve onto the main sequence, burning hydrogen, and enjoy a relatively peaceful existence until they run out of fuel. When this happens, the stars undergo a complex evolutionary dance, evolving into giant and supergiant stars, before ending their lives in either a beautiful planetary nebula or a violent supernova explosion. At the end of a star's life, the least massive stars, like our Sun, become white dwarfs, while medium-mass stars become neutron stars, and the largest stars become black holes. Together, these three classes of objects are some of the densest things in the universe and make up the universe's mysterious stellar graveyard. White dwarfs, neutron stars, and black holes can be observed by astronomers if they interact with other luminous objects, such as in tidal disruption events, where a star is torn apart by a black hole, and accretion flows, where white dwarfs and neutron stars cannibalize their companions, or from their temperatures, such as hot young neutron stars that are visible with X-ray observations. However, since these are dead stars, they don't actually produce their own light, and so most of the stellar graveyard is really hard to see. These are super interesting objects and can tell us about the fundamental physics and astrophysics of our universe. We want to be able to probe them in detail, and that's where gravity, our invisible messenger, comes in. Because stars exist in binaries, we would expect to find black holes and neutron stars in binaries too, and that's exactly the case. And when two galaxies merge, the supermassive black holes at their centers eventually form a binary as well. Binary systems of dense objects in the stellar graveyard, like black holes and neutron stars, produce our universe's strongest gravitational wave signals. This is GW 150914, the first detected gravitational wave signal in a binary black hole system. In a binary, the objects are orbiting each other, and that means they're constantly accelerating. Due to their high densities, they create really strong gravitational waves. The black holes start out pretty separated, but as they emit these gravitational waves, they lose energy and spiral inwards, eventually resulting in a catastrophic collision. This entire time, the fabric of space itself is carrying information towards us about everything happening. These ripples in space mean that space is actually being stretched and squeezed as the waves pass by, and so things get closer and farther apart. These distances are tiny. At Earth, they're 1,000 times smaller than a proton. In our galaxy, we have hundreds of pulsars. These are neutron stars that emit radio beams which sweep across our line of sight like a lighthouse, producing pulses. They're extremely regular rotators, and so we can almost exactly predict when we'll see the pulses. The most regular rotators of all are special pulsars called millisecond pulsars, some of the fastest spinning objects in the universe. However, when a gravitational wave passes by, the space is stretched or squeezed, meaning the distance between us and the pulsar changes. Because light takes time to travel, pulses arrive slightly ahead or behind schedule, following the pattern of the waves. Just one pulsar can't detect gravitational waves alone. It takes many pulsars in the galaxy, spread out like flies on a web the size of the galaxy, to sense the tiny ripples in space-time. This is done by precisely timing the arrival times of pulsars' pulses in what's known as a pulsar timing array and measuring how they deviate. Pulsar timing arrays such as the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, are trying to detect the background signal of gravitational waves that comes from supermassive black hole binaries trillions of times the mass of our Sun. These ripples come and go over the course of many years and change pulse timings by less than nanoseconds. Astronomers all over the world, including in your backyard, aim to precisely track hundreds of pulsars and will one day be able to learn about the growth of galaxies and black holes in the universe from gravitational waves. In fact, pulsar timing arrays can tell us about things like the turbulence of gas and dust between the stars of our galaxy, the true nature of gravity, the demographics of supermassive black holes, the formation channels for neutron stars, and even the existence of theoretical cosmic strings. Within NanoGrav's mission, I personally work on research related to pulsars and have characterized radio frequency interference in pulsar observations, developed algorithms for finding special pulsars that turn on and off sporadically, called rotating radio transients, and studied the population characteristics and microphysics of peculiar events called pulsar glitches. Aside from NanoGrav's pulsars, gravitational waves can also be detected with giant lasers, such as the Laser Interferometer Gravitational Wave Observatory, or LIGO, and the future LISA mission, which will operate in space. So far, LIGO has seen dozens of black hole and neutron star mergers and is beginning to probe everything from the fundamental physics of black holes to the expansion rate of the universe. Today, astronomers are even searching for gravitational waves in the cosmic microwave background, or CMB, the light frozen in time from our universe's earliest days. How can you get involved? Gravity Spy is a project improving the LIGO detectors by helping machines learn the difference between actual black hole signals, like on the left, and glitches or detector noise, such as on the right. Anyone can participate and contribute to improving LIGO's ability to detect our universe's most mysterious signals. Pulsar searching is a huge deal for NanoGrav and pulsar timing arrays, since adding more pulsars increases the sensitivity, and the collaboration aims to use nearly 200 pulsars by the end of the decade. The Pulsar Search Collaboratory connects high school students and teachers with astronomers and allows them to help search for pulsars with radio telescopes. And if you're ever not using your computer or laptop, Einstein at Home allows you to contribute your unused computational power for searching for pulsars with Arecibo. Finally, for undergraduates, NanoGrav, LISA, LIGO, and other gravitational wave collaborations have institutions all over the world, many of them in the US funded by the National Science Foundation. Just a handful are shown on this slide. Astrophysicists are always looking for students to contribute to interesting and important projects. And aside from research, school astronomy clubs and local astronomical societies are amazing resources for learning about space. I really can't express how exciting the possibilities are. We've seen the night sky with light for millennia, and with particles for decades now. Gravitational waves are an entirely new way to learn about the universe, and in conjunction with the exciting next decades of observational astronomy, the era of gravitational wave astronomy will be like turning on the sound to the movie of the universe that has been silent up until now. Thank you.
Thank you so much, Christine, for that insightful and inspiring presentation. We truly enjoyed learning about your astronomy research. If you have any questions for Christine or just want to reach out, be sure to reach out on her social media. Or you can email us your questions at samamishtscn@outlook.com or DM us on our Instagram at samamishtscn, and we would be happy to connect with you. All of it will be linked in the description below. And thank you to everyone who joined us today. We truly hope you enjoyed this talk. As this is a series, we have to shout out our next talk on Tuesday, August 11th at 4 p.m. PST. We have a talk from the amazing Nathan Apfel on listening to the mind. Be sure to join that talk and the many more to come during the summer on Tuesdays at 4 p.m. You can stay up to date with us on our Instagram, and be sure to subscribe to our YouTube channel. Thank you all once again, and stay safe.